one, boost ignition, and liftoff of the Space Shuttle Discovery, returning to the...
Hello and welcome to Across the Kármán Line. I'm Aditya Varma, and today we have two very special guests with us, Adrian Nixon and Debbie Nelson. Adrian is a graphene and 2D material scientist working with Stellar Model. He's the editor-in-chief and the director of Nixene publication, and is also on the board of the International Space Elevator Consortium. Next, we have Debbie. Debbie is the Business Development and Marketing Communications Manager at Nixene and is also the Director of Communications at Stellar Model. Thank you so much for coming, guys. How are you?
Really good.
Doing well. Thank you. Yes, happy to be here.
So let's start with the very basics, because I am a complete beginner in graphene. So I have absolutely very minimal idea as to how the world of carbon works. So what exactly is graphene, and how did both of you come about getting involved in the graphene sector?
Yeah, Debbie, do you want to answer that? And I'll be your glamorous assistant.
I'm going to take that that lead and just share that I became involved with graphene when I had seen it on the radar of someone that that I followed, and they were paying attention to it. So I started paying attention to it and trying to find out what this was all about. Some big fancy advanced material. So I found out that graphene is a single atomic layer of carbon, and the way that you isolate that, you have to take graphite. Well, you don't have to. There's a couple of ways. So you take graphite and you use an exfoliation process. There are a number of ways to do it. You can do it anything from water to harsh chemicals, and of course, with the sustainability, everyone's leaning towards all of the green ways to obtain graphene, and that results in platelets in like a graphene powder that can be easily mixed into things. You can also create graphene from a new technology out of Rice University in the United States, where you basically zap it with energy, and it can break apart all the bonds. And when that happens, with carbon likes to reassemble itself, and then it makes the honeycomb pattern that Adrian has a very cool model of that we use as a cover on the cover of our Nixene journal. So I think I've hit the high points. Adrian, did I miss anything?
Yeah, it's pretty good. Apart from the fact that Rice University can make this stuff from waste plastic, can't they, Debbie?
Yes, they can. They can do it from just anything that has carbon in it. Yeah. So, and there's an awful lot of research happening right now that's very exciting. So we're looking forward to talking about that later.
Yeah. I suppose we could talk briefly about the properties of this stuff, Debbie, as well.
Oh my gosh, I don't know all 9 of them, Adrian. So we actually had a chart, and yes, there were 7 up until 2 years ago, and or last year, 2 years ago, when 2 more were added. So we have the strongest material known, we have the highest electric conductivity, we have the most impermeable, and we have, I'm going to forget, so help me, Adrian.
Highest melting point of any material?
Yes, highest melting point. Where are we at? 4 or 5 now. We need our chart.
We do indeed, yeah.
to pop it up for our viewers. Yeah, we could send you a chart over to pop in for the viewers. But
world's best conductor of heat and electricity, 200 times stronger than steel, flexible, transparent. What else have we got, Debbie? You mentioned impermeable, even to hydrogen, although you need 2 layers of graphene for that. And 1 layer of graphene is impermeable to helium. 1 atomic layer of graphene is equivalent to a kilometer thick glass wall in terms of impermeability. Yeah, as a physicist, Aditya, you'll appreciate that is pretty spectacular.
Yeah,
it really is.
It's also pretty much untearable, and it has the highest fatigue resistance of any material known.
That was the one.
Nice.
Yeah, it's not bad.
Yeah, definitely.
We call them the graphene superlatives because there really isn't anything better than that. So
yeah. So I mean, the primary purpose of being on this call today is because there's a lot of more recent talk about the use of graphene in the space industry and how it's aiding the revolution. So we can just start off with your most recent take on where we're headed, how it's used in the industry, and how it's being considered the future of the space revolution.
Mm-hmm. Debbie, do you want to start off and I'll pick up?
I can definitely share what we've been doing as far as graphene in space. We actually have a publication, which I'll shamelessly plug real quick, which is called Graphene in Space, and it's available on our website. But it's a collection of the various kinds. What we do is we monitor research that's coming out. It's at the last count, there were 129,000 papers written on graphene each year, and so sifting through and really curating that kind of news to find the things that are really going to stand out is what Adrian does every month. So we have all kinds of things on technology and also on applications for space. So the tech that's been coming out and actually has converted into applications as things like graphene oxide membranes for water purification. And let's see, Orbex is a good example. The rocket company in the UK that uses the largest 3D printer in Europe to print their rockets uses a carbon fiber and graphene composite for their main system in their tanks, which is pretty impressive considering we don't hear a lot about things like that are coming out. A lot of people have these secrets that they're keeping to themselves, but we're pretty confident that there's a lot more in some of the other places that we haven't heard of yet. There's one of the things that I want to mention too is that like we noted before, we are part of where we were invited by NASA to speak at their commercial lecture series. And it's a vetted audience of a lot of people in the business and NASA and rocket scientists and things like that who talk about the commercial viability of all different approaches for space. And we were able to spend some time talking about it. Adrian did his the talk on graphene and what more he's going to talk about with the space elevator. So Adrian, you've got to get some words in here about how you got into graphene and all that. So
that was a good start, Debbie. Yeah, there's a ton of things that graphene is being used for in space applications. Debbie's mentioned the Orbex launch vehicle. So this puts microsatellites up into orbit. They're about a kilo, that sort of size, Debbie, sort of a liter.
Yes.
Square. It's the sort of thing that Elon Musk's Starlink, I think, is made of. These little CubeSats and things. Yeah. But the carbon fiber body is enhanced with graphene. Now, what that does is you can, by adding graphene powder to the epoxy resin, as you mix it in with the carbon fiber, then it turns the carbon fiber composite into something which has much higher impact resistance. It's 30% stronger, so it means you can use less material for the same strength. So it's a lightweighting. Yeah. And as you're probably aware, Aditya, there's something called the rocket equation, which is the mass on the launch pad. I think, is it about 0.5% of the mass on the launch pad will reach the surface of the moon or Mars. So the amount of weight, or the amount of mass, more precisely, is really important. Anything you can do to reduce that is critically important for space applications. Debbie and I, sorry, go on, Aditya.
I'm sorry. I was just saying, I'm also assuming it would also add to like the cost efficiency of the projects, given how large scale rocket-based projects are becoming now in terms of space exploration as well.
Yeah, yeah. The composites aren't used as widely as they could be at the moment because Elon Musk has chosen to go down. Is it stainless steel he makes his rockets out of?
I am not sure.
It's steel.
Yeah,
it's definitely steel. Yeah.
And that's because he wants to reuse them. And you can, the defect testing in the tanks is quite well known, but with carbon fiber composites, these are laminar structures that are laid down, sometimes with 3D weaving in them, but the fatigue detection inside these structures is still, it's developing because we've got lots of aircraft flying, but for space applications, you want to be absolutely, totally 100% and more sure that this stuff is okay. So reusing composites tends not to be a big thing at the moment. However, Debbie and I are dealing with, we're talking to a guy called Vivek, Debbie, aren't we?
Yes.
And
Yes, I thought for sure Vivek was going to come up today.
do you want to mention roughly what he's doing, Debbie?
Oh, he has, he started out doing a graphene rubber composite that would take recycled tires and create mats and flooring that was it's basically indestructible. I think it would take a very long time to wear out his product. But he's expanded into creating actually a space station. So it's a very exciting shift to go in. He has funding. Everything is underway right now, and it's very exciting. It's an expandable kind of a design. So everything with graphene, because like Adrian mentioned, it's the one superlative I can't believe that I forgot, because that's key to space, is you're making everything lightweight, like you said, so that you can reduce the cost of everything, make sure that things are light to go up, and you can bring more.
And if you want to find out what he's doing, the guy is called Dr. Vivek Concherry, and he's based at the same place we are, the University of Manchester. He's based at the Graphene Engineering Innovation Centre called The Geek.
Yes. If I'm not wrong, I believe you did have a talk with with Dr. Vivek as well, right?
Yep.
About space habitats. Yes. I like that. We'll add that link in the description.
Oh yeah, do.
Well.
Yeah.
Yeah.
And
Yes.
Debbie, we have a YouTube channel, don't we, where we put all our videos, and we're quite happy to share any of the links with you guys.
Yeah.
Yeah, absolutely.
So one thing that I was wondering was in terms of how these materials are being used in space. A lot of the times, like just going back a little bit, it's very hard to visualize a two-dimensional material being used in terms of building stuff, right? So could you just talk a little bit about that, how like that is used, how like we use graphite structures and like take individual layers and then create a structure out of it that's as big as, let's say, like you mentioned, the space elevator and other stuff.
We've talked about powders so far, haven't we, Debbie?
Yes.
Just before we go to the space elevator, could we just stick with powders a little bit more? Because everything we've talked about so far is powders. We haven't talked about large area sheets yet. But the one thing before we leave powders to mention is concrete, Debbie, into building materials and regolith.
Yes. So using, one of the things that's happening right now, especially over in the UK, they've poured concrete that's been enhanced with graphene and come up with some phenomenal results. You mix the graphene in the powder, and you don't just dump a lot in. You work on getting that formula exact, and that's where a lot of people went wrong at the beginning. They dumped a lot of graphene in and didn't get the results they wanted. Well, they've come up with a way to balance it out so that when you use graphene, you actually can reduce up to 30% of the materials that you use. So your cost is reduced, and the results are extremely strong. And that's part of what we're talking about for space, is going in and being able to use the regolith to mix with whatever fluids are on hand. And so, of course, everything in space has to be recycled, reused. And there's a lot of work going on with that as well.
And it turns out you can make something called polylactic acid, or PLA, from urine. So the astronaut's urine would normally be a waste product, but you can turn that into a kind of polymer that you can use. PLA is actually used to 3D print things, but you can also use PLA as a binder for regolith. The problem is that the UV radiation tends to break it down. So if you add graphene powder, and by the way, here's some graphene that we accessed earlier, just a black powder, as Debbie says, add a tiny amount of that to the polymer, and it stops the regolith from breaking down under UV light. So you can start to build structures on the surface of other worlds that you get to, which is quite cool. There's a ton more stuff we could talk about, but as Debbie said, just adding it to normal concrete, you can add 0.01% of that black powder I've just shown you. You make concrete 30% stronger, so you can use 30% less material for the same mass, for the same strength of structure on Earth. And as you're probably aware, Aditya, cement production accounts for 8% of global CO2. So you could probably take 2% off global CO2 by using less concrete for the same structures without any of us changing our lifestyle at all today. And that we're just scratching the surface, aren't we, Debbie? What graphene?
We really are. Yes,
yeah.
yes, it's very true.
Yeah. So we've reached the point where we've talked about powders, and probably we could go on and spend a whole 2 hours talking about powders, but that's probably good enough for you at the minute, I would think.
Yeah. So let's move on to a slightly more recent development in terms of space elevators then, which is something that you've been involved with more recently. And so firstly, what exactly is the space elevator? How is like the organization going about with the design and structure, and where does graphene come into the picture? And also, like, is there an alternate, or is it like the most efficient way, or like the iterations that have gone into reaching the point where graphene is playing a role in it?
Right. Debbie, do you want me to do that, or do you want to start off with something?
I'd actually like to start off with something, just
it.
because, you know, when I was invited to join Nixene Publishing, and we were talking about graphene and what it applies to and things like the space elevator, I thought, all right, these guys are, that just sounds so far-fetched. I've got to look this up, you know? So when you go in and you start exploring the concept of a space elevator, you find out that NASA has studied this thoroughly. And then they had to set it aside because they didn't have a suitable material for the tether. And amazingly enough, the following year, Andrei Geim and Kostya Novoselov, yes, they sat playing on a Friday night, you know, with some sticky tape and some graphite, and just, you know, kept peeling it off till they got graphene. And, you know, the single atomic layer, they used this known kind of an experiment, something fun. So this material that you've got to look at the timeline and say, you know, that's incredible that it was discovered the very next year, that after NASA set it aside. So in the meantime, with all the developments and all the experimentation and all the research with graphene, then you come into the fact that they've had the International Space Elevator Consortium working. What, has it been 7 years, Adrian, or longer?
Longer, yeah.
Yeah, yeah. And they have a chief architect, and they've put it, all this has been studied so thoroughly. So there's no way that I could not get involved. It's way too exciting and very just world changing. So
yeah. So this stuff isn't science fiction. It's pretty close to science fact. As Debbie said, NASA was one of the people that actually came up with the idea of the space elevator. Quite a few other people have been playing with it over the years, but NASA really threw a lot of effort in. So we just explain roughly what a space elevator is and how it works. The Earth turns, obviously, on its axis, and you can if you launch a rocket up with a geostationary satellite, then the rocket goes up and it goes sideways to match the rotation of the Earth. And then it will deposit a geostationary satellite. And for the sake of argument, if it was above you, then if you looked up, you would, if you had a big enough eye or big enough telescope, you would see that satellite above you all the time, and it would never move relative to the surface of the Earth because it's spinning the same speed that the Earth moves. So now the idea is, if you get a cable, Debbie said it's called a tether, and you drop that piece of material all the way from the satellite down to the surface of the Earth, you've now anchored a point on the Earth with a point in space. And now you can clamp onto this and pull yourself up. And like Jack in the Beanstalk, you'll be up in space. And it's a lot safer, and it's a lot more environmentally friendly way of accessing space. Does that sort of make sense so far?
Yeah, absolutely. So like you mentioned, like a geostationary satellite. So what exactly would be the end point, or like the terminating point of the elevator? Like where, like what point in space does it lead to?
Right, okay, really good question.
yeah.
So you need to think about how the physics of this works. So as a physicist, you'll understand this probably far more deeply than I am, because I'm a chemist. But here's a chemist's explanation. So if you can imagine, you've got like a bucket on the end of a piece of string. Dennis Wright, one of my colleagues, explained it this way, didn't he? You know that if you half fill a bucket full of water and you put it on its side, the water falls out. Yeah. But if you tie a string to the handle and if you spin round, then centrifugal force will carry the bucket out, and it will try to go off in a straight line, a tangential point all the time. But the string that you're holding is pulling it back in to an orbit all the time. Mm-hmm. So you're going round in circles. So relative to me, the bucket is staying still. And that's roughly how the space elevator works, except it's anchored at the equator, because that's where the Earth is spinning fastest. And the piece of string you have to substitute for a tether. Now, something interesting is going on, which breaks down the metaphor of me with the string and the bucket, because we've got gravity involved. Mm-hmm. And we've got very big distances. So that distance from my hand to the bucket is from the surface of the Earth right out to a counterweight. And that is about 100,000 kilometers distance. So big stuff. Yeah. That counterweight is just a mass of something fairly big. And we'll park what that is at the minute, but it's just enough to keep the whole thing taut in strength. Then, as you come up about 30,000 kilometers from memory, you reach geostationary orbit. So about a third of the way along, you'd have a geostationary platform space station, and the material would go from the surface of the Earth through the geostationary space station right out to the counterweight. And so we have a number of components here, and NASA actually took apart all these individual components, didn't they? And they did a feasibility study, and they threw several million at it. And as Debbie said, it reported in 2003 that everything you could make the space elevator out of, the stuff on the Earth, the stuff on geostationary, the counterweight, the space station, everything else was doable with today's technology. And the climber, the lift cage that goes up, or the elevator cage, that was all doable. Except the only problem was the only materials that were available were things like Kevlar and stuff like that, or steel, and they are either not strong enough or too heavy. They would break apart under their own weight. And the only material that was available, which was strong enough and light enough to do the job, was carbon nanotubes, another carbon form. And at that time, carbon nanotubes were only available to be made in millimeter lengths, and you need lengths 100,000 kilometers long. And the technology effectively stalled. And as Debbie said, that study concluded in 2003, carbon nanotubes, the best stuff to make the tether out of. The tether is the limiting factor. It's a materials problem, nothing else. And at the moment, we can't make it long enough, therefore the project stalled. And then, as Debbie said, 2004, Debbie, graphene was first isolated. And then graphene was now a new material, as it was strong enough and light enough to make the tether out of. And since 2004, some amazing things have been happening. Now, Debbie, I know that you've got to go in a minute.
I do.
So do you want to hang on any longer, or do you have to make
I'm gonna stay for like about 5 minutes longer, because you know how it is when we get talking about this. And I hate to peel myself away. I have to today. Yeah.
Okay. Do you want to say anything else, Debbie, about the space elevator and the materials so far?
I was just going to emphasize the fact that, you know, the technology that was available that NASA decided it could be done was 2003. You know, that's a considerable amount of time. So imagine now what can be done, you know, better, stronger, and all the rest of it. And we come with graphene. So now we know that graphene could be used for a lot of those things that we've already talked about that NASA could already do back then, now that we're looking into graphene composites with carbon fiber and, you know, metals and things like that. So
I need to clear up something for the viewers, because even the experts get this wrong. So we've been talking about graphene powder so far, and Debbie's quite eloquently showed us how that gets made from either waste plastic or graphite or whatever, and that's doing amazing things. Now, the next form of graphene is the same material, but it can be made on larger scales. And the way this works here, you'll have to take my word for it, Aditya, but on the surface of that copper foil, there is a 1 atom thin layer of graphene covering the surface. And that is probably about, what, 7 centimeters square already? So that is pretty much a single molecule covering the whole surface, which is quite cool, really. Yeah. I mean, it's not perfect yet. There are grain boundaries in there, there are vacancies. But fundamentally, this is now where the state of the art of the research effort and industrial effort is going. Debbie, do you want to explain how that CVD process works and what CVD is? Or
here's what I know. All right, I can quote to you. So in the laboratory, they create graphene by setting it up with the carbon to be able to make the single sheet. Now they typically put it on a copper foil. It settles down into copper foil, and that gives it a substrate. It has to have some kind of substrate, and then the current problem is getting it off the substrate to be able to have a single layer of graphene without a substrate, and that's what the big challenge is at the current time. And Adrian even has some interesting information about things like that. So,
right. So,
pretty good.
Thanks, Debbie. That's good. So, what we have, just a quick recap: we've got a piece of copper foil here. We get methane gas, or methane, as they say in the States. So CH4. So 1 carbon with 4 hydrogens. Get it very hot. Bring it down close to the surface of the metal. And the metal does 2 things. Debbie said it forms a flat surface on which a 2D material can rest, but also the metal acts as a catalyst and allows the hydrogen to come off. The carbon lands on the surface, and then once it's on the surface, it forms this chicken wire arrangement, the hexagonal form, because that's the lowest energy conformation that it can form. And so all of the things being equal, everything will settle down to the lowest energy place it can. So now we've got carbon covering the whole surface, 1 atom thin. And as Debbie said, the trick now is to get that carbon graphene layer off the surface without damaging it. 2 ways: some sticky tape, but then it's stuck to another surface, or you can dissolve the copper. There are a number of other ways of getting it off, but that's the process at the minute. Now, you can see here, I've got 7 square centimeters there, which is pretty large for a molecule, because we're used to thinking molecules in terms of nanometers. Now, let's think about the space elevator tether. This has to be a single piece of material which goes from the surface of the Earth out to 100,000 kilometers. That's 100 million meters long. And to take full advantage of graphene's or carbon nanotube strength, but we'll stick with graphene for the moment because this is where the technology is most mature. So to take full advantage of that, you have to basically form a tether from layers of graphene all stuck together. At ISAC, we're working on the design for the tether, and we reckon 500 mil wide, and it will be 12,333 layers of graphene laid on top of one another. Each one of these layers is a single molecule that goes from the surface of the Earth out 100,000 kilometers, which is pretty wacky for a molecule. So the question is, can graphene be made fast enough and long enough to actually even begin to think about layering this stuff up? And the answer is, surprisingly, boy, yeah, we're getting there. The industrial manufacture of graphene has just run, it surprised us, hasn't it, Debbie?
Yes, absolutely. It's exciting to see what can be done.
So the industrial manufacturing process now has moved to the point where we've got reel-to-reel or roll-to-roll manufacturing of graphene. So at the moment, this starts off with copper foil, and you have 1 reel of copper foil, and then you put it through a furnace, and it gets reeled up at the other end. And in between, that furnace deposits graphene on the surface, and you can form, at the moment, it's polycrystalline graphene, but they're working towards making single crystal. And the speeds and the lengths that are available now are astonishing. So the various, while Debbie and I have been working on this over the past, 2 years at least, Debbie, several secret projects have come out into the open. And as Debbie said, we're reporting on this continually. We've got, there's In the USA, Debbie, there's a company called General Graphene. Do you want to say a little bit about them and what they're doing?
Sure. General Graphene is a spin out from Oak Ridge National Laboratory, and they have the ability to commercially produce roll-to-roll graphene. It's polycrystalline, and what I wanted to mention is Adrian had said earlier that vacancies and various defects exist on polycrystalline, as opposed to a single crystal graphene, which would have 0 defects, and is the goal for the tether. So,
and then in Korea, just to go on a little bit more about General Graphene, Debbie, they've got the capacity to make 100,000 square meters per year on their latest generation 3 machine of graphene. I mean, this is only since 2004 when it was first isolated, and before that people thought graphene was impossible to exist even as a 2D material. So we've now got industrial manufacturing on this scale. Hardly anybody knows about this yet. Then in Korea, we've got LG Electronics. They're looking at they've got another roll-to-roll process. They can make graphene at speeds of 1 meter a minute already, which when you think about it, that's pretty impressive.
Yeah.
And then there's another manufacturing company called Charm Graphene, again in Korea, that can make graphene by another roll-to-roll process at speeds of 2 meters a minute already.
Okay.
And so you can see the trajectory we're on. We're going faster and faster and faster. This is atomic engineering at meters a minute speeds already. We only need to increase the speeds by another factor of 60 to get down to meters per second, and to get to the speed range where it actually becomes feasible to make these incredibly large lengths of material and get the quality up too. The pace of development is just astonishing, and you could see over a 5 to 10 year time scale, this stuff is just going to take off and do amazing things. So
if I could interject really quickly, because I'm going to have to go, but I wanted to say that as the pace increases and industry realizes what the uses of the CVD graphene are, and how it applies, that it takes it even makes it more exciting in the fact that when silicone was discovered, it took 35 years for it to get out to market like this, and we've done this in half the time. So it's a very exciting, very fast-paced, very we're just defying an awful lot of what we really used to believe about science and physics and molecules and things like that. So I will leave you two gentlemen to discuss the rest, and thank you so much for having me here today.
Thank you so much. It was an absolute pleasure.
Bye, Debbie. So ISAC is the International Space Elevator Consortium, and I'm a member of the board of directors. ISAC is a not-for-profit organization based in California and the States, but it covers the world, and anybody can become a member. So if any of your audience out there is interested in joining ISAC, then if you go to the website isac.org, and that will take you through, the links will take you through, and you can contact the organization and you can find out and get the inside track on latest in graphene materials, latest in space elevator design. And the people you'll be talking to are real rocket scientists. These are the variety. The people I work with are astonishing. It's multidisciplinary teams. We got everybody from chemists, physicists, rocket scientists, engineers. We got people who've built bits of the Large Hadron Collider and the Stanford Linear Accelerator. So you're not sharing space with a bunch of crazies. These are proper world-class guys, and you can join them if you want.
Yeah, oh, absolutely. ISAC is it's been very fascinating. Like it's been a constant topic of discussion over the years at KCL Space as well, because some of our past members have been interning, been involved in some way or the other. So yeah, definitely. So we'll put the link down in the description for ISAC as well. So check it out if you're interested.
And it'd be good to maybe do some mutual links as well between the two organizations. I'd be happy to do that for you.
Absolutely. Yeah. So now I think more towards a little bit more towards the side of how to get involved in something like this, because again, it's a very up and coming field still, and things are changing very rapidly. So what would your advice be to students just starting off in the field, or just anybody who has an interest in the field?
It depends if it's the science, the engineering, the economics. ISAC is probably a very good starting point, a gateway to this. There are a number of organizations around the world. We know that China has a space elevator program, but being China, it's sort of, you only hear bits of it from time to time. There's a lot more going on behind the scenes than most of us realize. China wants to have a space elevator operational by about 2050. I think that's one of their declared ambitions. So if you are in China, then you would have to contact your usual sources of information to find out who to get to. I don't know who's working on that in China, because that's close to me. In Japan, you have the Obayashi Corporation. They are working on the space elevator. I think they have a slightly faster timescale. They're cooperating with ISAC. So if you want to find out about Obayashi in Japan, ISAC is probably a good place to go. I better not make any comment about what's going on the military side, because the space elevator isn't really a military thing. It's a static piece of infrastructure, and you don't really build it for military advantage as such. You build it for economic advantage. So that's another one of the good reasons to work on this stuff. So civilian organizations are probably the way to go. Watch what's happening on LinkedIn. If students are on LinkedIn, there's a lot of activity there. The difference between sort of LinkedIn and Facebook is the people on LinkedIn tend to reference the material, and it's a little bit more robust, a little bit more business orientated. So whereas the people on Facebook, you're not quite sure of the validity of various sources. So for example, I don't really inhabit Facebook, but you will find me on LinkedIn. And quite a lot of the people I move with are LinkedIn. You could watch what's happening on the American universities side of things. The European Space Agency, some members are beginning to wake up to this. We know NASA is waking up to it because they asked us to talk to them about it. And they asked us specifically to brief them on the progress of materials for the space elevator. What's happening in these big space organizations is you've got some people inside these organizations who get what's happening and say, yeah, space elevator is now doable. But you've got some old guys who are still stuck back in the old days saying, no, this is really science fiction. Rockets are the way to go. The interesting thing is the rocket scientists fall into two camps. Ones that realize that the space elevator is not a competing technology, it's a parallel technology. So you need both rockets and a space elevator. And the reason for that is rockets will get people up very fast, and they'll take you through the radiation belts very quickly. A space elevator, current technology at the minute, and the people I'm working with reckon we could probably take about a week to go from the surface of the Earth up to space. That's about 200 kilometers per hour up to geostationary. That means you're hanging around in the radiation belts for an uncomfortably long amount of time. So for the minute, we can think about it as a goods lift for taking mass up to space. And that's something rockets can't do. So Elon Musk, Jeff Bezos, people like that, they want to build factories in space and on Mars. It means taking millions of tons up into from the surface of the Earth out elsewhere. The problem is, the people I work with, I tell you, the rocket scientists, they've looked and calculated how much mass we've taken from the surface of the Earth up into orbit in the history of mankind, and it is 26,000 tons. And that includes the military launches. When you think about it, it's not a lot. And so when Mr. Musk, who I admire greatly, talks about shipping hundreds of thousands of tons of material up there, it's probably possible, but boy, the impact of that many rocket launches, when you've got a tiny amount of mass to take from the surface of the Earth up, is going to become a limiting factor. And people will start to realize that as these things scale. The space elevator doesn't suffer from that. It can take massive amounts of mass up and do it in a very green way as well, because you would solar power the thing. So you wouldn't have the pollution you get with massive amounts of rockets.
That's true. Yeah, absolutely. So any target dates that the ISAC has in mind, or like a year that by when we can like potentially see this starting to become a full blown out construction project?
We're talking at least a decade more research to get the materials to the point where we can actually get really big pieces of tether material made, and we can start to play with this. A little bit longer, probably somewhere between 1 and 2 decades, I would say, to get a functioning space elevator going. It really all depends on the will. So if you threw resources at this, it's amazing how quickly things can change. You know, you think about the space program, putting people on the moon was thought to be impossible. And yet it was done within a decade, wasn't it?
Absolutely.
From starting. A similar principle could apply to the space elevator. At the minute, if we carried on the way we are, you would never ever achieve anything because there's hardly any resources going into this. But we've done the costings. I'm working with a study group within ISAC, which is studying the climate tether interface. So we're actually looking at, in detail, the engineering, the science, materials, and energy to actually get to build this and then make it operable. And all the rocket scientists I'm working with say this is doable. And you've already seen that the limiting factor is this tether material. And what I've given you is a little bit of an insight into how fast, how big the industrial scale manufacture of graphene is shifting. Hardly anybody realizes this at the moment.
Yeah, that's true.
You follow that trajectory and you'll be making graphene at speeds of meters per second at costs of cents per square meter, probably within a decade.
That's very cheap, very cost efficient as well. So it wouldn't even be a resource heavy investment.
Yeah, and at the moment, you know, it costs a fortune to get that stuff onto the copper foil, but economies of scale kick in and you get mass production, and you've just got the will of governments around the world cooperating together, throwing money at this, bringing the brightest brains together. There's a heck of a good start being made within ISAC. I've got the inside track on this. I know what's happening, and these guys have pretty much nailed a lot of the big problems. And the biggest thing that we've been addressing is this actually doable? And if we did it, is the material climbable? And the answer to both of those questions is yes. It's closer than you think.
Yeah, definitely. I'm assuming most of our viewers would be able to see it within this lifetime itself.
Yeah.
So I think that brings us to the end of the scientific part of the discussion. Before we conclude, this is just something I like asking. So 2 questions: who's been your role model, or the person who you look up to, who's gotten you into the field over the years, and 1 book that you'd recommend to the viewers, 1 book that shaped you into going into the field that you're in?
Wow. Do you know what? I don't really have heroes as such. People I admire, probably Richard Feynman. I mean, you as a physicist who would probably sign up for that one. He's a really smart cookie. And a lot of the stuff that he's been working on is still relevant today, probably even more so. So yeah, I don't really have heroes, but if I had to pick one, probably be him. And he seemed like a fun kind of guy too.
Absolutely.
Yeah. So, and the other one was a book. I'll stick with the space elevator book and recommend Arthur C. Clarke and the Fountains of Paradise.
Perfect. Again, the link to both books and more on Richard Feynman and his work also down in the description. And with that, we've come to the end of this episode. Thank you so much for joining us, Adrian.
It's been a pleasure.
Thank you.